And let's start going through the exercise number 2. So exercise number 2 is about systems. And there are some questions. First, about linear and time shift invariants. So fundamentally, those linear and time shift invariant systems are the ones which are in our scope for this course. Okay, so nothing else than that. We are not too much interested about causality or well, stability is in our interest, but it's easiest to check from the zeros and poles. Okay, then there is a difference. Well, let me expand this a little bit. So there is a block diagram. You need to figure out what is the difference equation, meaning what is the output. Then you need to figure out how to generate the parameters bk and ak, which are also called system coefficients or system parameters. Okay, calculating the zeros and poles. Then again, A and B for this system, zeros and poles. Then combining systems. So we have the parallel system. What is the combined system coefficients? Combined systems again in series, meaning cascaded. Maybe I should. In cascade, it's the correct term. Q3 and 4, 6. Again, then we have a feedback. We have a negative feedback of Q3 for the system Q6. What is the combined system coefficients? Okay, and then is the system stable? I have a bad feeling that it's not going to be stable, but you will see. Some of you actually will get unstable systems, but yeah, that's the whole trick here. All right, let me go first through how to check if the system is linear on Octave. And I'll show you that one in so by describing a system as a function. So let's see. For example, a system where the output is simply x of n minus 0.5 times x of n minus 1. So how to make this kind of system? So this is the system that we are going to test for linearity and time shift invariance. Okay, simple enough. Would someone tell me if you have already done your own functions on MATLAB? Remember that, how to write your own functions. That's pretty easy, actually. Okay. Let's create a new function. Hey, there you go. You have a prototype. And what I usually do here is who cares about the beginning stuff here? There we go. And this function we call myfunc, it has only one input, which is our input XX. So practically, this is only function of one input, and inside of that one, we actually tell what the output is. And here, the return value is simply XX plus, oh, right, or was it minus? Minus 0.5 times x with an index of -1. Ooh, there are ways to do it. One way is actually that you will delay the XX. We combine a vector which starts from XX2 to the end length. Hey, wait a minute. Is that way or the other way? -1. Not. I'm always getting confused about that one, but length of XX and then add 0 to the end, since we don't know the, wait a minute, XX2, sorry, yep. Actually, it goes like this. So we take, on the first, for the first XX output we are calculating, we actually are calculating that we know only the current value. We don't have the history yet. Okay, so for the first initialization value for the first XX value is 0, and then we shift. Wait a minute. Do we have a operation shift? I think we have. Circular shift. Haha, that will do. X and 1, and this is circular shift. It doesn't matter. It does the shift. It just produces also an artifact. Shift by 1. Okay, we use it only here. You usually don't do these kind of things with shift operation, but I will mark it here. Usually you would use either use filter command to do the shift. But here we don't know that filter exists, so we just shift the data by one time delay here. Save. Now we can call the function. And for that one, I can actually do, for example, something like that. XX equals to random numbers, 100 random numbers. For example, 100, and then we can plot. Let's do the index vector. And then we can stem, for example, the n xx looks like that. It's a random vector, and when we do a we can calculate the output using the previous function, myfunc xx. And then for the same plot, stem yy. I don't know if that is actually smart. I think I'll just stem plot that one. Okay, it looks about the same. If you want to actually compare these compare the plots, you can actually use either hold on and hold off, which means that it then just changes oh, it holds the plot, and then you can plot something, another plot on the top of it, or you can actually also have, for example, something like that. So we are dividing the plot into two rows, one column, for example here, and pointing the first one first. So we stem xx there, then we call subplot 212 and stem again output. Now we can actually compare those two plots, input and output. Okay, it looks like that actually somewhat works. At least it gives some numbers. Now let's check for the linearity. Linearity check. And what does it say about the linearity? When the system is linear, if and only if that one is true. So let's see what happens if I, no, it doesn't. Ah! Oh, great. What happened here? Syntax error. Yeah. I copy pasted. Okay. Parse errors and such kind of things. That was fun. So linearity check. So we practically calculate two things. We calculate this part first. Which is the left-hand side of the equation. Doesn't really copy. It doesn't really copy paste. Great. I did it again. And now I broke the octave. Did I? No. Left-hand side. Okay. Let's try that one again, but with some care. Function, whatever that is, a times x1 plus b times x2. There. And for that, I actually need two test vectors. Oh, wow. First one. for example, 100 random points. Another one is also 100 random points. This test is an engineering test, meaning that it does not prove mathematically anything, but it works. So using a long enough random signal sequence, you can make actually pretty nice predictions on if the system does work or not. So we simulate and calculate if that left-hand side part of the equation is the same as the right-hand side part of the equation. And for that, I have x1 and x2. Then I need a couple of coefficients or yeah, cascading values. Okay, just one random number. And BB is random number. Again, random number. And those are different random numbers, I think. Yeah. Wow. Is that exactly one? Wow. That's strange. Let me try to get some other random number so it looks more random. AA. Yeah. Now AA and BB are different random numbers. Okay, and now we can calculate the function output, which is YYL, like left part, is my func. AA times XX1 plus BB times XX2. That's the left-hand side. The right-hand side of the equation was right. A times function with the input x1 plus b times function with the value x2. Okay, and that would be YYR. A times my func XX1 plus BB times my func XX2. Okay, left-hand side and right-hand side. Are they same? Okay, we have 100 values in a table, which means that they are vectors. When two vectors are the same, distance is 0, meaning norm of the difference. Strange. Norm of the difference is 0, then okay, I found an artifact. I've wrote there history shows that norm of the diff, and here I have only norm O shown up. Okay. So difference same as norm. I need to now first check what is the norm. Documentation, function index, norm. Okay, second, I think second norm is used if the second argument is not given. Let's see, let's test. difference or distance between these or error is then norm of YYL minus YYR. Ha! Not zero. Why is that? Let's check what is the machine epsilon. This is using double precision, the floating point numbers, and our machine epsilon is 2.2 times power to minus 16. I would say that this value what we got is close enough to machine epsilon so that this difference is actually zero. It's very, very, very small. 50 minus e to minus 15, that means femto. Okay, these particles or the atoms are something like 10 to minus 10. If this was meters, this would be subatomic level. So small. Very, very small. Okay. DD. So practically is zero, which means that difference is zero, which means that system is linear. Okay, great. That's how you check if the system is linear. Then the other one was about time shift. If the system is time shift invariant or not. There we can actually do similar test. First, time shift input values. So we calculate the output using time shifted input values, YY, capital I, like input value is shifted, and we calculate it for my func and shift. Okay, XX, how much? Well, any arbitrary number actually will do. It doesn't make any difference here. For example, 2. Time shift. Okay. Oh, I see the command window. I think I have only 40 characters there. Then it doesn't show. I need to fix something here. But anyways, let's fix this set first. Okay, and then next I will calculate the output is shifted. So we shift my func XX by 2. The same shift, but for output. And we calculate then the difference again. DD LTI. Ha, 0. So it didn't mean anything if I shift the input before or after the function. Okay, good. So that's how you do this exercise. although you need to be very careful when you are formulating the function. So practically, when you're doing the function, it must be so that there is only one single input argument. So the function is the function of input only. If there are any other stuff, like in this case I have, you do not have this the value 2 as the input variable, but you have that one inside of the function. Okay, that's straightforward. And here you have only x as your input value, not e to power of n. So where do you actually then determine inside of that function that e to minus n? You need to generate that n inside of the function using the information what you have. So when you are calling a function like I have here, I actually know that the indexes for xx would be from 1 to length of xx. So you cannot feed in the n to that formula. All right, so that is the hints for the first two parts. Then the third part is how to determine the difference equation. Let's see, okay, let me see if I can actually get one drawing. Okay, I will open it on a diagrams. You have open diagrams. By the way, if you want to draw nice diagrams on this for Google Documents, this works pretty well. So it's the draw.io, and there we are. Text. Font color. Red. Apply. So practically how you actually do this kind of exercise is what I already showed you. So on this point is 0.5 times x of n. At that point, we have x of n minus 1, since we have this one delay. Okay, good. Here we have x of n minus 2. At that point, we have y of n minus 1. Okay, and here duplicate that one. Still the same here. After that one, we have 0.5 times x of n minus 2, and so on. So fundamentally, in this case, y of n would be 0.5 times x of n plus x of n minus 1 plus, and so on. So you practically just follow the signal, and you can little by little form the equation. So, and that's the difference equation for this system. Let me see if I can actually divide that one into two. So for here, the difference equation itself would be y of n equals 0.5 times x of n plus x of n minus 1, oops, 1 plus 0.5 times x n minus 2 continues on the next, and then we have point plus 0.2 times y n minus 1. Okay, for the difference equation parameters, remember the let's see. Difference equation as the sum form. So this form here. The parameters are defined such that they are positive when you move all the parameters with all the terms of y on the left-hand side. So practically the difference equation, the same as before, then is yn minus 0.2 yn minus 1. So there is a sign change here, which is part of this coefficient here. There. Good. So system coefficients. System coefficients are defined from this form of the transfer function. So for the as an answer to the fourth example for 4, the we can define the parameters AA equals system coefficients for the output, which is, well, 1 times y of n. Then there is a minus 0.2 times the y of n minus 1. Then actually you can also imagine here a 0 times y of n minus 2 if you want to. And then the parameters b, which are the denominator polynomial coefficients, or they are the parameters for the feed forward term 0.5. Oops. Not there. Oh, great. 0.5. Point, not comma. 0.5, 1, 0.5. So the most common mistake on this exercise is to have a sign error, since you have determined the system coefficients from the difference equation, that you just follow the signal through the system, but then you don't remember to move this part to the left-hand side, which is how we define the whole transfer function and the system coefficients. There we go. So just don't do the most common mistake. But now we have the system defined. And after this, everything is simple, since these are the same coefficients in difference equation and transfer function, meaning the same coefficients can be used both in time and frequency domain. For example, calculate zeros and poles. Zeros are the system zeros. So zeros are actually roots of polynomial defined by B coefficients. Okay, so we have double root at -1. Yeah, good. Poles are the locations of roots defined by denominator polynomial. 0.2 and 0. System is stable. That those both roots are inside of the unit circle. I think, let me see if I get the error message here. Z-plane, BB, or wait a minute, let's take the documentation Z-plane. Cannot find it, so it means that I have to load signal and control. Let's see, documentation. Do I find the Z-plane now? No, I don't. Search. Yeah, there is a Z-plane. Good. So for Z-plane, you call it, okay, Z-plane B and A. Okay, good. Z-plane B and A. This is basically almost Argon's diagram. If you just plot that one into the as an answer, then that's just fine. So 0 pole plot. Oops, it goes in the small window. Okay, 0 pole plot is here. We have double 0 at point -1 on real axis, and then we have these two poles inside of the unit circle. That's unit circle. Great. So, so basically, this is system is stable. Since the norm, let's see, the absolute value of roots on the poles less than 1. Yep. So basically, yeah, 0 and 2. Absolute value meaning the distance from 0. Okay, good. So system is stable. Then the following determine the parameters for A and B for this following system. Okay, that's fine. Okay, there's another system. Let me take an example. Another simple system. So let's see. I'll just throw the BB equals 1 and minus 0.5. And then, okay, this is the second system. I have two systems. 2 equals 1 and 0. Actually, what is the difference equation for this system? Okay, y of 1 times y of n. I will write it here. 1 times y of n plus 0 times y of n minus 1 equals 1 times x of n plus, or is it minus 0.5 times x of n minus 1, or actually, let's see, I think this is quite familiar. Actually, our function returns those values. But now we have defined it different way. We have just defined the parameters for the output term, which is simply y of n, oops, not 0, n. Then we have 1 times x of n here, and then we have minus 0.5 times x n into 1, which is shifted x1. Okay, good. So we have this function which returns actually those values, although that was a circular shift. Doesn't matter. Now we can use these to represent the system. Good. So what to do with it? For example, we can now zeros and poles for this system would be Z plane BB2 A2. Ha. Okay. Yeah, first order system, it has one pole at the origin, and which means it's stable, and then 1, 0 at point 0.5. Good. Now I have two systems, both stable. And how to combine systems in parallel? Okay, parallel meaning adding systems. And we have two polynomials. Wow. Now I would need some mathematical tool to show what is actually going on here. But you know how difficult it is to add rational polynomials. You have probably done it already on the signals course. So adding two the rational polynomials, which basically means that first you need to make to have a common denominator, meaning the denominator is basically the when you multiply the denominators together, and here how to multiply of polynomials. Oh, wow. Is the same as convolution of parameters or convolution of coefficients. So the denominator for, so now we have the h1 of z times h2 of z times h2 of z, and both are basically the form of the not multiplied, but sorry, add common denominator. So basically we have, how does it go? Numerator 1 times denominator 2 divided by denominator 1 times denominator 2 plus numerator 2 times denominator 1 divided by, need to continue here, numerator 2 times denominator 1 divided by the common denominator. This is how it goes from mathematics classes. Okay, well, that does not look that bad, since the multiplication of these polynomials are actually same as convolution of the parameters. So the total system okay, that's the same as, let me put this one here again, equals there. Good. So numerator equals convolution of numerator 1, which was bb, with the denominator of 2, which is a of 2, plus convolution of numerator 2, which is bb2, with denominator a. There we go. That's, oops. Is it conv? Sorry about that, convolution. Yeah, sorry, it's not convol, it's conv. And then the denominator for that is simply conv of AA and AA2. And those are the numerator and denominator coefficients of the new system. So basically, AA parameter is the parallel is the denominator coefficients, they are there, and then BB of this parallel system is the numerator. There we go. I had some values. Excellent. Actually, since this has both numerator and denominator actually have the last value is 0, it means that this is second order system, not third order system in reality. But anyways, this is how you mathematically do it, brute force. And this would be a correct answer. And now we have the parameters again. We can take a look at the for example, that zero pole plot. Wow, it's totally different. So we have two zeros, they are not on the unit circle anymore. And then these poles are actually at the same place. Okay. So that's how you calculate these parallel system coefficients when you have a system which has feedback. For non-feedback systems, it's easier to combine, since then you automatically have the same denominator polynomial, which is simply scalar 1. So you then need to just add these numerator coefficients together. But since we had a feedback term, it immediately changes this one. A little bit cumbersome operation, but on the other hand, it's not that bad. So simply you just need to have a common denominator, meaning that you multiply with the first term with a first transfer function h1z with denominator 2 divided by denominator 2, and vice versa to the second the transfer function. And the total transfer function parameters, the octave does the rest. It's just like that. Okay, combining systems in Cascade, that's easier. Since then on cascaded systems, we have H1Z times H2Z, which is simply, okay, I'll just mark it like that, BB cast equals convolution between BB and BB2. It's simple multiplication of the numerators. And AA cascaded terms will be convolution of AA and AA2. Ha. So this is how you cascade this, or calculate these system coefficients for the cascaded system. Simply convolute the numerator terms and denominator terms, and to see if this is still stable system, you can take a look at the z-plane. And yes, it is stable. There's 1 0 here, but the location of zeros do not mean anything for the stability. Only the location of poles define if the system is stable or not. Okay. Feedback. I will leave that one for you to figure out how to calculate the system total combined system coefficients. There are enough of tools for you on the lecture part, the last 3 slides practically, which shows how to combine, play with the with these system blocks. Practically in here, one way to do it. Let me open. Is just follow the signal. I will show you a little bit here. If in this point I had x of z, Then this would be y of z. Here we have on the output, we have Q3 of z times y of z. Okay, I think you got the idea now. If you just follow the signal, at here you have the x of z minus that one, and y of z here is actually Q6 times the this difference. You'll find the yz, you find you have the xz, you can then calculate yz divided by xz, and then you have this nice polynomial form of rational polynomials. You may want to use some pen and paper to calculate the denominators and numerators so that you get everything correct. But you have all the tools necessary to do that exercise too. Wait a minute. I'll leave that one. Okay, so that's the whole show for today. I hope you enjoyed a lot. I did. And yeah, any questions? I will be still here for 15 more minutes answering any questions if you have. Otherwise, you can start working on the exercises. And as usual, I actually recommend you to team up. These are not easy exercises. They are not meant to be easy. If it was easy, somebody else would do it. Non-engineers would be able to do it. This is called engineering, applying mathematical tools to solve real-life problems, like this problem with the wait a minute here. Problem with how actually this cascaded system, is it stable or not? Analyzes if a system is stable. You need to be able to calculate the zeros and poles, especially poles. Are the poles inside of the unit circle or outside of the unit circle? And that defines if the system is stable or not. Okay, great. Now I shut up and let you two ask questions. And maybe I will stop also recording.